Okay, so what do we know about statistics?
It's a bell curve.
It's a bell curve, okay.
What else? Starts with an S.
Okay. Standard deviation. So all of those are statistics. Those are measured standard deviation, mean, bell curve as a density. But what does the field do? You know, we talk about data science a lot. We talk about statistics a lot. But what does the field do?
It kind of like predicts.
Prediction is one. But
Quality control, maybe.
quality control, another. That's a field in and of itself. And most important part here is, you know, modeling. You know, not in the Calvin Klein sense, but modeling in the sense we want to come up with a model, a mathematical model. But using random data, random, some people like to call it stochastic. If you get into economics and finance, one of those things, people like to call it stochastic. Suppose I give you a bunch of points. Yeah, give me a bunch of x values.
0, 1, 2, 3, 4.
0, 1, 2, 3, 4. Okay. And those are the y values. So consider an experiment where I've observed those x values, and I've observed those y values, or I'm observing the y values for those specific x values. So in algebra, we call that the response variable, and that's the predictor or the explanatory variable. If I asked you, based on the pattern that you observed, can you give me a model, a mathematical model?
1/2 X.
Huh? 1/2 x. Do we agree? Yes. If you plug these in for every single value, we actually know that this particular equation is going to work. And that is a linear model. You were able to capture this information without any issues because, you know, there wasn't variation at all. Things were very deterministic. You plug in 0, you get 0. You plug in 1, you get 0.52, you get 1. So based on practice, you're able to come up with that model right away. Here is a navigate. So 0, 0, 1.89, 2.64, 3, 2.9, 4, 1.75. Tell me, what would the model be? So easy, right? Can you give me more?
Not immediately.
Not immediately. You could probably do a bunch of math and, come up with more. Yeah, something like that. Right? If we had visualized that data, what would it look like?
A straight line.
That would be a perfect straight line, right? This is not a perfect straight line. These are observations scattered around on, the XY plane. But this is an experiment or a process that I observed, and I would like to understand this process. And these are the measurements that I'm getting. I plot it, and that's what I see. And there is no meaning to the naked eye, right? But I want to somehow quantify and come up with a model here. Does that make sense? And that's where statistics comes into play. So
You usually find the best fit there.
we call it random because there isn't a strong underlying pattern, a deterministic pattern in the sense we can't simply draw a line. Points are scattered across the XY plane. And why does it happen? Well, it does so because
Real life never makes anything easy for you.
I'll call it some A and X, right? And then I'll add a B. We all know what that is. That is the equation of the line. What is the value of A here? A is half. B, 2, 0. So that is deterministic, right? It follows that pattern. Now, what makes it random? That epsilon. What is that epsilon?
Expectation.
Good try. That's what we call noise. When noise is added to a deterministic process, you end up getting a random process. It's that simple. Right? Now, what do we mean by that? Let's say you're doing some sort of research with turtles, and you go about measuring, say, the width of their skull. Do you believe that? Let's even fix. Let's measure the width of the skull with respect to age. Do you believe that the width of the skull will be deterministic based on the data that you collect?
I think it would be like within a certain range, is
Do you follow the example that I'm using here?
because of fossils. I thought you had fossils, not turtles. Okay, well,
No, turtle. So age, let's say 30, 40, 20, 30, 35, 40, 42. They can live for a long time, right? I don't know what the width of a turtle's skull is going to be. Do we know?
Depends on the turtle.
It's probably small.
Huh?
It's probably small.
There are some really big sea turtles.
Let's say in centimeters or in meters. This is hypothetical, don't look this up.
Not even one.
So 0.5, 0.78, 0.42. That is huge, right?
Yeah, it's probably,
Oh, I meant to say,
yeah, centimeters.
50 centimeters, 52 centimeters, 50, even that's.
Yeah.
Yeah, 100 millimeters. 64, 72.
They're probably about like 4 inches.
Let's just millimeters. This is not real. I'm making this stuff up. But understand the example there. So this is a case where I have age and width. Width would be the y variable. Age would be the x variable. Because the width of the skull is going to be explained by age, not the other way around. Correct. If I change the skull width, would the age change for the turtle? No, but as the turtle grows older, the width of the skull will change. Right? So here, width would be y, and age is x. That said, we could put a similar model y equals ax plus b. You look at that, do you think that is a very deterministic line? No. This has variation in it also. Why do we call it, random? Because of the noise that gets added. But there is an underlying truth. Do you agree? If you can measure the perfect turtles that are born in this world, the entire world, and everything worked, without any perturbation, without any randomness added to them, it'll be a very deterministic case. Yes, you can take one turtle's age and predict it right away. So the underlying model of ax plus b it is the true model. That is what we're trying to model. But unfortunately, the truth is unknown. Correct? Do I know everything about turtles and their skull widths? No. So this is unknown. The true model is unknown, but using this data, which is random, I am going to find the values of A and B. Good. Let's say I found the values A and B, I end up getting a model. Let me quickly do a regression here. So if I get y to be equal to 1.46 plus 13.76. Now I use R. You can use your calculator too, right? 2023 linear regression, it's in your calculator. So I did fit a model, and I was successful in fitting this model based on this data. So 30, 52. Suppose I went around and caught another turtle, estimated age to be 30. I can plug it in here and come up with a value. Do you think that whatever value I come up with will be 100% accurate? No. Even if I predicted, say, somewhere over here, 32, I can plug it in here, I would come up with a Y value, start with. I go, somewhere and get a turtle whose estimated age would be 32. What measurement that I measure would it equal whatever the model gave us? Will it? No. But if we have a good model, this value will be very close to that. Do you agree? Yes. Provided this is a great model. So our objective is to come up with a model that could be really, really good so that you get close to the truth. In statistics, you can never be 100% confident. You can get closer to the truth, but we never know the truth because the truth is, the process is random. So the underlying truth, no one knows. But based on the data that we see, we can get closer to that truth. And if I went and collected a different set of data, let's say I went from 5 turtles to 10 of them, would I get the exact same model? No. And things would change, but if consistently I keep getting different batches of turtles and I get consistently values very, very close to these two, then somehow that range becomes the truth. Right? Do you agree? So, hypothetically speaking, I collect another batch. I forget that model, say n equals 5 turtles, 10 turtles, 20 turtles. I can repeat this process. So if I ask you, well, can you make an estimate about the truth? What do you think? Just an estimate. A reasonable one, based on these 3 different batches. Can you give me one? A reasonable estimate for the truth. What would that value be?
Something similar to the past, or something similar to what you found.
Yeah, but what do you think would be reasonable for A?
1.48 maybe.
1.48 may be the truth, right? Because it's somewhere here. And that could be about 15.9. So if I repeatedly get the same information time and time again, then you're getting closer and closer and closer to the true model. But even after 1,000 different batches, you haven't found the truth. You're only getting closer to the truth. See the difference? So our objective is to find the true model because the data is collected by models. So here, got all this variation, and if I ask you to come up with a model that will describe all of these points, where would that line be? Could it be that line?
No.
Could that line describe all 5 points really well? No. Nowhere close, right? Could it be that line? No. No. Well, where should the line be?
Right in the middle.
Right in the middle. Right. And that is what we call line of best fit or the regression model. So we made use of random data. We ended up getting a line of best fit. Does that make sense? And the process, the statistical method that is behind this is linear regression, which is why we call it a regression model. Now, does that line describe the truth behind this process? No. No. That could be close, who knows? But our objective is to get closer. We all know about the scientific process. When we come to a conclusion, we're not saying this is it. We're rather saying, based on the evidence that we observe, this is what we have, and we are pretty sure about this, but a good scientist always knows that if new evidence comes along and if it changes things, then you have to accept that change, right? Because that's what data's giving us. That's why we say we never know the truth. I think that is a good place to stop.